Okay, so following our discussion on reversible and irreversible processes, there is a very important theorem by Carnot, and this was proposed in 1824. Carnot described a reversible engine that is operating between two energy reservoirs. So there is an ideal reversible engine. Now here is Carnot's theorem. So Carnot says no real heat engine that is operating between two energy reservoirs can be made more efficient than a Carnot engine. And this engine has to be operating between the same two reservoirs. Okay, so basically Carnot says, theoretically, the maximum possible efficiency that you can have for an engine that is operating between two energy reservoirs is that of a reversible engine, which is called the Carnot engine. So here is the scenario. We have two energy reservoirs, hot reservoir at temperature TH, cold reservoir at temperature TC. There is a real heat engine which is absorbing heat QH from the hot reservoir and releasing heat QC to the cold reservoir and doing some work W. Alright, so now we pick another engine, a Carnot engine. This is a reversible engine, so it can be operated as a heat pump or a heat engine. So if you operate it as a heat engine, it would basically absorb an amount of heat QHC from the hot reservoir. It would provide an amount of heat QC Carnot to the cold reservoir, and then it would give you a work W when operated as a heat engine. When it is operated as a heat pump, it will absorb heat from the cold reservoir, provide heat to the hot reservoir. So this is the absorbed heat, provided heat, and then it would also require some work to be added to the engine, that's W, in order to operate it as a heat pump. Alright, so we have other engine. Other engine is irreversible. We have Carnot engine that is reversible, and W output of heat engines are the same. So I have two engines that provide me the same amount of work. So basically I'm addressing the efficiency of these two engines, which one is more efficient than the other one. Okay, so I'm going to call Carnot engine efficiency is EC. Other engine efficiency is E. Okay. Assume that the other engine efficiency is greater than the Carnot engine efficiency, and these are both operated as heat engines. Okay, so as a heat engine, what is the efficiency of the Carnot engine? It's going to be the useful output W divided by the energy that I have to input in order to achieve this task, and the other engine efficiency would be W divided by the heat it absorbs, QH. Now, since I assumed that the other engine is more efficient, then I'm going to have W divided by QH is greater than W divided by QHC, which is telling me that the heat absorbed by the Carnot engine must be greater than the heat absorbed by the other engine. Okay, so if I write the first law of thermodynamics for these two engines, for the other engine I have the energy input QH that is turning into the work done, and part of the energy is provided to the cold reservoir, QC. And for the Carnot engine, I have the energy absorbed, QHC, is turning into the work plus the heat released, QCC. So I see that if I subtract the first equation from the second equation, so this is going to imply that QHC minus QH is equal to QCC minus QC. So I have to have this equation between these two, the heat absorbed and the heat released. Now let's think about what this equation is telling us. Because I have QHC minus QH is positive, this basically is a positive quantity. So the heat that is absorbed by the Carnot engine is greater than the heat absorbed by the other engine. The heat released by the Carnot heat engine is greater than the heat released by the other heat engine. Now, what I'm going to consider is the Carnot operated in the heat pump mode. So, Carnot as a heat pump. So what does that mean? That means it is absorbing heat QCC and releasing heat QHC, right? So there is QCC being absorbed. Now at the same time, the other heat engine has a QC that is less than QCC. So since QCC minus is positive quantity, it appears that I can replace this set of two engines, the heat engine providing work W to the Carnot heat pump, can be replaced with an equivalent engine, such that the total amount of heat this engine is absorbing from the cold reservoir is QCC minus QC, and the total amount of heat this engine is providing to the hot reservoir is QHC minus QH, and they are both positive. And you see here there is no work, so basically the equivalent engine is a heat pump that is absorbing a positive amount of energy energy in the form of heat from a cold reservoir and providing the same amount of energy to a hot reservoir without any work input. Equivalent engine operated as a heat pump. The equivalent engine is a heat pump. Well, what do we know about this result? This is not allowed. Why is this not allowed? Okay. The equivalent engine violates Clausius statement. So, according to the second law of thermodynamics, Clausius statement, you cannot build a heat pump that is going to absorb heat from a cold reservoir, release same amount of heat to a hot reservoir without energy input in the form of work. So therefore, my assumption was incorrect. The other engine cannot be more efficient than the Carnot engine. So the Carnot engine, what makes the Carnot engine special? That it is reversible. A reversible Carnot engine is always going to be more efficient than any other real heat engine that is operating between the same two reservoirs and providing the same amount of work output.